Assalamu alaikum. Bismillahir Rahmanir Rahim. I welcome you to the 43rd lecture for the series of lectures on advanced computer architecture. Today, the focus of our discussion will be internetworks and clusters. After a brief review of what we discussed last time, we will be talking about what are the basic features of internetworks and clusters. In our earlier lectures on networks and clusters, we discussed the formation of interconnection networks and their categorization. We also discussed the network communication model, its performance, media, software, protocols, subnets, and network topologies. In our discussions, we noticed that the basic interconnection network comprises computer nodes, hardware and software interfaces, links to the interconnection networks, and communication subnets. The interconnect communication model shows that two machines are connected via two unidirectional wires with a first in, first out buffer at the end to hold the data. The communication software separates the header and trailers from the message, and it identifies the request, reply, and their acknowledgements, and it also performs the error checking. The communication protocols suggest the sequence of steps to reliable communication. We also discussed the properties and performance of interconnect network media, which is also referred to as the link. These medias include the unshielded twisted pair or UTP, coaxial cable, and fiber optics. The formation of bus and switch-based communication subnets were discussed, and we introduced the network topologies. While talking about the bus-based communication, we noticed that the subnets share the common media where arbitration is the only bottleneck. However, we noticed that the alternative to sharing media is the use of switch that provides a dedicated line to all the destinations in order, and it facilitates point-to-point communication much faster than the shared media. Furthermore, the switch-based networks are classified as the centralized switching networks and distributed switching networks. Here, we noticed the routing to establish interconnection between two nodes at a time depends on the addressing style. So these addressing styles are either source-based routing or the destination-based routing. Furthermore, we studied the performance of distributed networks, which is measured in terms of the latency, which is the number of links between source and destination, and it is also measured in terms of the bandwidth, which is the number or length of message passing per second, and the degree of nodes is the number of links connected to a node. The other metrics are the diameter, which is the number of nodes between source and destination. This is indeed the measure of maximum latency also. However, we also talked about the bisection and bisection bandwidth. Bisection is the imaginary line that divides the interconnect into roughly two equal parts, each having half of the nodes, whereas the bisection bandwidth is the volume of the communication which is allowed between any two halves of the network with equal number of nodes. While talking about the networks, last time we discussed an intermediate class of networks interconnect known as multi-stage switch networks. The multi-stage switch network is built from a number of large switch boxes where each switch box contains number of small crossbar switches. Here we notice that the performance of multi-stage switch networks lie between the performance of non-blocking crossbar and the bus-based networks. Then last time, following the discussion on the centralized switch topologies, we studied the distributed switch interconnects, where these interconnects are categorized as the fully connected and partially connected interconnects, and these interconnects may be symmetric or unsymmetric. The distributed switch interconnect topologies are a linear array, ring, 2D mesh or torus, and hypercubes. We studied these topologies in detail last time. Now, so far, we have been talking about the design styles, the topologies, and performance of interconnection networks. Now, today, we are going to talk about the connection of two or more interconnection networks. That is, so far we have been talking about the interconnection of computers only. But now we are going to talk about the interconnection of the networks. Now, this interconnection of networks is basically referred to as internetworking, or in general, we also call it internet. The Internetworking basically deals with the communication of computers on independent, incompatible networks, and it must give us the communication with reliability and efficiency. Now let us study the internetworking. The internetworking basically relies on the communication standards. These standards are used to convert information from one kind of network to another kind of network. These standards are composed of hierarchy of layers, where each layer is responsible for a portion of overall communication. Here, each computer, network, and switch implements its layer of standards, and the software which implements the layer of standards is known as the protocol families or protocol suites, and it facilitates applications to work with any interconnection. However, there are different models which exist for the communication. The Open System Interconnect, or OSI, is the basic model which is developed as a 7-layer model. This model describes a network as the series of layers with the application layer at the topmost level, which is usually the layer 7, and the physical layer at the bottom level, that is, it is layer 1. And there are number of other layers such as the presentation layer, the session layer, transport layer, network layer, and data link layer. These layers lie in between the top layer, that is the application layer, and the bottom layer, that is the physical layer, in the same sequence as I have mentioned over here. The OSI model layer 7, the application layer, is used for applications specifically written to run over the network. For example, the network file system, that is NFS, etc. Whereas the layer 6, that is the presentation layer, it translates from application to network format and from network to application format. The 5th layer, that is the session layer, it establishes, maintains, and ends the session across the network. It means that this layer is responsible to first establish, and once the interconnection is established or the communication is established, it maintains it. And when the communication is finished, it ends this communication. The layer 4, which is called the transport layer, it facilitates additional connection below the session layer. That is, this protocol is referred to as the transmission control protocol. The layer 3, which is called the network layer, it translates the network address and their names to the physical address. For example, the computer name to media access control, the layer 3 protocol is also referred to as the Internet Protocol or IP. The layer 2, which is the data link layer, is responsible to turn the packets into raw bits, and on the other side, that is at the receiving end, it turns the raw bits into packets. The example of this protocol is Ethernet. Whereas the bottommost layer, that is layer 1, which is called the physical layer, it transmits raw bit stream over physical cable or physical media. However, this is in fact the IEEE 802 protocol of the physical layer, which is followed at this stage. The protocol family basically divides the responsibilities among the layers, with each layer offering service needed by the layer above it. For this purpose, the transmission control protocol and internet protocol, that is TCP/IP, is the most popular internetworking standard, which means that for the internetwork communication, basically it is the transmission control and the internet. These two protocols are very, very important, and they are forming the internet networking standard. The TCP/IP is the basis of internet, which connects the tens of millions of computers around the world. Let us see how the protocols are being implemented at each level. The protocol at each level is in fact implemented by adding a header and a trailer at the sending end or at the sending layer, and these headers and trailers, they are removed at the receiving layer. Here in this case, the original message from the top layer, it includes a header and a trailer sent by the lower level protocol, and the next lower protocol in turn adds its own header and possibly the trailer also to the message, and this way it moves from the top layer towards the bottom layer. If at any stage the message is too large for a particular layer, then it is broken into smaller messages. This division of messages and addition of header and trailer continues till the message descends to the physical transmission media. The message is then sent to the destination. Now, each level of protocol family at the receiving end, from the bottom to the top layer, it checks the message at its level and it removes its header and trailer and pass it on to the next higher level. This message is rebuilt by putting the pieces together, and this way the whole communication is established. The nesting of protocol, this nesting, that is placement of one above the other, this nesting of protocol layers is usually called protocol stacking or the protocol stack, because it reflects the last in, first out nature of addition and removal of the headers and trailers. Now you can have a look onto the TCP/IP datagram. Here, this datagram shown over here is a standard IP and TCP header, where each TCP and IP header is of 20 byte in this particular diagram. However, the length can optionally be increased, which is specified by the field, as you can see in the leftmost side, second to the left one, which is marked by the field L. The length of whole datagram is identified by a field length in the IP header, whereas the TCP header also includes this information in the sequence number field shown here. However, now I have introduced to you the basic internet working protocols, but I would like to mention here that the detailed discussion onto the TCP IP and its complete communication is in fact beyond the scope of this course on computer architecture. Therefore, I will be leaving this discussion here, and from now onward I will be talking about the clusters. However, if anybody is interested in the further study of internetworks, they may consult literature and books on computer networks and internetworking. Let us now discuss what is a cluster. A cluster is also referred to as the system area network. To define a cluster, we can say that the coordinated use of interconnected computers in a machine room, which means that when there are massively large number of computers present in one room and they are interconnected together, it forms a cluster. This is why a cluster is also referred to as system area network. Here, the massively parallel machines providing the bandwidth can be built from off-the-shelf components. So we can say that the clusters can be built from off-the-shelf components instead of depending on the customized machines or custom networks, which are usually made for massively parallel applications. A cluster can also be defined as a collection or bunch of desktop computers and disks, such that it offers low-cost computing infrastructure that could tackle very large problems and applications, such as these applications are the databases, file servers, web servers, simulation, and multiprogramming or batch processing. The clusters face some performance constraints. These constraints are non-standard connections and division of memory. Let us talk about these constraints one by one. First, considering the non-standard constraint, we can say that usually the multiprocessors are connected by using memory bus, which offers high bandwidth and low latency. Contrary to this, clusters are connected using input-output bus of the computer. Therefore, it gives large conflict at high speed, and its latency is very high, and it may have a smaller bandwidth. Similarly, the division of memory can be explained such that a large single program running on a cluster of n machines requires n independent memory units and n copies of operating systems, which means that if we have a cluster of n machines, then there will be n copies of the operating systems onto the hard disk of each machine, and each machine is having independent memory unit. Whereas, on the other hand, a shared address multiprocessor allows to use almost all memory in a computer, which means that the total memory is available to one program, whereas in case of cluster, memory is divided. So it gives us the degrading of the performance. However, contrary to these challenges, the clusters have some advantages, and these advantages are in respect of the dependability and scalability, which means that the clusters offer high dependability and higher level of scalability. The weakness of separate memories for the program size in case of cluster, as discussed earlier, is indeed a strength in terms of systems availability and expandability, or say the scalability. Furthermore, as the cluster consists of independent computers connected through a local area network, and a cluster software is a layer that runs on the top of the local operating system. Therefore, it is easier as compared to multiprocessor to replace any computer without bringing down the computers in the cluster. Hence, a cluster offers high dependability and at the same time the scalability. With this much introduction about the clusters and its merits and demerits, let us study the cluster design. Now, in order to study the practical aspects of cluster design, we will be considering an example of cluster which is made by using 32 processors, 32 gigabit DRAM, and 32 or 64 disks. Now, for different cluster designs, let us consider a Pentium 3 processor, which is, say, operating at a clock rate of 700 megahertz or 1000 megahertz, and it includes a large level 2 cache, which is, say, ranging from 256 kilobyte to 1 megabyte. However, note that due to the large die size, which becomes large due to the large memory size, the processor memory chip price with 1 megabyte cache is almost double as compared to that of the processor with 256 kilobyte cache memory. Furthermore, in cluster design, the higher price of chip matters very little, but the objective is to minimize the cost for a desired performance target. This means that, in fact, while designing a cluster, it is not important to take into consideration the chip price only. Rather, we are interested in designing the cluster such that the overall cost is minimized to achieve the required performance. For this purpose, we will be considering 4 different cases, and we will see how different designs can be developed, and then we will analyze the performance of these designs. These 4 cases are the design for the cost of cluster hardware with local disk, and the second is with disk over a storage area network or system area network level. The third is the cost of the cluster options, that is more realistic options, which means that in addition to the option for the cost only, we have to take into consideration the other options also. And the last one is, while talking about the design examples, we will be considering the cost and performance of a cluster for transaction processing. This means that whether it is efficient on the processing and the transaction or not. So for this purpose, let us first of all consider an example. In this case, we would like to develop the concept of designing a cluster for the cost of the cluster hardware with local disk. For this purpose, let us consider 3 different organizations of the cluster. Number 1, a cluster made of uniprocessors, then a cluster which is made of 2-way symmetric shared memory processors, and the third one is using 8-way shared memory processor cluster. Let us first of all consider the design of a uniprocessor cluster. Uniprocessor cluster organization is shown here, where you can see that it consists of 32 computers of IBM series 300. Now, in these computers, there is some built-in memory available, and we have to see how this memory is going to fulfill our requirement. Now, in the machine which we are considering for our design, the maximum memory available is 1.5 gigabyte per computer. So this means that we can easily achieve our target of having 32 gigabyte memory by using 32 machines. Furthermore, as each computer in this series has got 2 disk drives, and each disk drive is of 36.4 gigabyte, so it provides us 2330 gigabyte storage area, which is indeed beyond our requirement. Here, the organization uses the built-in slots for the storage devices, so computer can accept its own gigabit hard adapter. Hence, we need only 32 cables which are to be connected to the Ethernet switch. However, one thing is to be noticed over here. The switch indeed has got 30 ports only. So this, whereas we have 32 cables which are to be connected in order to connect 32 hard disks. So this means that now in this case, instead of using only one switch, we will require two switches to be used over here. As these two switches are to be connected together, it requires 4 ports, because as you can see from the diagram, 4 cables are to be used over here to interconnect these two switches together. So this leaves 56 ports out of 60 ports for 2 switches, and this means that these 56 ports are now sufficient enough to connect 32 computers together. Now the last component for the design of a cluster is the rack. The standard rack is of 19 inches by 30 inches by 72 inch in width, depth and height respectively, and it can accommodate 32 uniprocessor computers, 34 rack units. These 34 rack units contains 32 sections for disk or for computers and 2 for the switches. And thus this means that this design is quite cost effective. In the second example, where we have to use two-way SMP cluster, which means that here we are using the computers with 2 processors of series 330. Now this architecture is shown over here, where you can see that in this design everything is halved, which means that here instead of 32 processors we need only 16 computers, because each computer has got 2 processors. Moreover, instead of 2 30-port switches, now we need only 1 30-port switch, because in this case we have to connect only 16 cables. Furthermore, the rack size is also 18 RU instead of 44 RU in the first case. So whole of this arrangement therefore reduces to half. Now let us consider the 8-way SMP cluster design. Here the 8 processor computers of series 370 as shown here are used. Only 4 computers are needed, as each contains 8 processors. Therefore, it gives us the required number of processors to be equal to 32. The maximum memory of 32 gigabit is easily available over here from 8 computers, as each has got 8 gigabyte of memory. However, with 2 disks per computers, the 4 computers can hold 8 disks with maximum capacity per disk to be equal to 73.4 gigabyte. Hence, it is not sufficient to fulfill our requirements, and we need expansion storages which may be placed externally. So the expansion storage with 14 disks is needed, and in order to install all these things we need 2 racks, and in this particular case this system is therefore relatively bigger as compared to the previous ones. Now the price of 3 clusters with a total of 32 processors, 32 gigabyte memory and 2.3 terabyte disk is shown over here. Note that the network cost here decreases as the size of the SMP increases, and this is in fact due to the fact that the memory bus supplies more of the interprocessor communication. Furthermore, the 4 of 8-way SMP costs more than the 32 uniprocessor computers. So this comparison gives us how we can select a particular configuration of the cluster to obtain the required performance and with the minimum cost. Now let us consider the second example, where the second case is for the cost of cluster hardware using storage area network or SAN for the disk. Note that in the previous example, we set the disk local to the computer, which reduced the cost and space. However, it offered the following problems for the operator. That is, here there is no protection against the single disk failure, and the state in each computer has to be managed separately. Now, in fact, this thing results in system downstate on the disk failure. To overcome this problem, a RAID controller and fiber channel arbitrated loop, which is abbreviated as FCAL, is used as the storage area network. In this case, all the SCSI disks are replaced by the FCAL disk behind the RAID storage server. Note that the FCAL can be connected in a loop with up to 127 devices, so it fulfills our requirement. The price comparison for the 3 cluster designs using SAN are shown over here. Here you can see that the cost of storage area network also shrinks as the server increase in number of the processors per computer. And now let us consider the third example of the cluster design considering the other cost. In the first 2 designs, we considered the cost of hardware only. However, the software, that is the database cost, and hardware maintenance cost, that is the cost of the operator to keep the machines running, were not considered in the previous example. The other costs, such as the cost of backup tapes, the cost of space to house the server, are also to be considered. If we consider all these costs, then a complete comparison of the earlier 3 designs of clusters, including these costs, are shown over here, where it shows that the 2-way SMP using storage area network is the lowest in total price. However, over the 3 years, the cost of operator will be more than the cost of the hardware. Here in this case, we are considering the cost of the operator only for 3 years. So this means that the purchase cost of the old computer is to be reduced in order to reduce the overall cost of the system. Now let us discuss the fourth case, that is the cluster design for transaction processing. A comparison is shown here for the cluster having 32 P3 processors and using the same IBM components as well as the building blocks and switches which we employed in the earlier examples. However, the key differences here are in the disk size. Here we are using the small and fast disk. The other difference is in the RAID. The no RAID is required in this case, as in this case the performance benchmark does not include the human cost. The memory here is the maximum DRAM which is packed into the server. So each of the 4 8-way SMPs are stuffed with maximum of 32 gigabyte of the memory, which yields in fact 128 gigabyte. Now, summarizing the cluster design examples, we can say that as the cost of purchase is less than half the cost of the ownership, therefore the cost of hardware solves only a part of the problem. So this means that while designing a cluster, we have to take into consideration not only the cost of the processors, but we also have to take into consideration the cost of other components. Summarizing our discussion today, we studied internetworking as the connection of 2 or more interconnection networks to communicate reliably and efficiently. Internetworking relies on communication standards composed of hierarchy of layers. We studied that the Internet communication protocol families facilitate applications to work with any interconnection. We studied the transmission control protocol and Internet protocol, that is TCP/IP, which is the most popular internetworking standard. Having introduced the basic concept of internetworking, we discussed the computer clusters, which is coordinated use of interconnected computers in a machine room. Here we studied non-standard connections and division of memory as the performance confront of clusters. Furthermore, contrary to these challenges, we noticed that the clusters have advantages in respect of dependability and scalability. At the end, we studied the practical aspects of cluster design through 4 different examples. Now today, in fact, we have completed our discussion on almost all topics related to this course on advanced computer architecture. Now, in the following 2 lectures, we will be reviewing the complete course and we will also have some discussion onto some practical application cases. With this, I close the discussion today, and I say you Allah Hafiz till next time. Thank you.